Okay guys, this is the part 1 video for lesson 2.5, talking about complex zeros and the fundamental theorem of algebra. The objective is to factor polynomials with real coefficients using factors with complex coefficients. Alright, so we're going to be dealing a little bit with imaginary numbers in this lesson. So the two theorems that we want to review is the fundamental theorem of algebra and the linear factorization theorem. They're related in a way. The fundamental theorem of algebra says if you have a polynomial of degree n, then the polynomial has n complex zeros, real and non-real. Some of the zeros may repeat. The linear factorization theorem says if you have a polynomial of degree n, then that polynomial has precisely n linear factors, and some of those factors may be repeated. Alright, so in example 1, we want to write the polynomial function in standard form for a, b, and c, and then identify the zeros of the function and the x-intercepts of its graph. So the first one for a, we have f of x equaling x minus 2i times x plus 2i. And so what we're going to do first is write down what the zeros are. So to do that, we set the left-hand side equal to 0. So 0 is going to equal x minus 2i times x plus 2i. Set each factor to 0. So x minus 2i equals 0, and x plus 2i equals 0. So x is going to equal 2i, and x is going to equal negative 2i. Alright, and so my zeros are x equaling 2i and x equaling negative 2i. Alright, and then we want to state what the x-intercepts are. Well, both of these are non-real, so let me erase this. So since they're non-real, we're not going to have an x-intercept. Alright, so no x-intercepts because both zeros are non-real. Alright, now what we want to do next is write the polynomial. We want to write the polynomial in standard form. This is in factored form. Alright, so I'm going to erase this, and if you notice that this is a difference of squares here, so I'm going to have we're going to have x squared and then the middle terms will go away, so negative 2i times x, add that to a 2i times x, that goes away, so then we're going to have a minus 4i squared, and so x squared minus I squared equals negative 1, so 4 times negative 1 equals negative 4, so this is going to be x squared minus a negative 4, so this equals x squared plus 4. So that's what the polynomial is going to be written in standard form. Okay, now this is part B here. Oops. Alright, and we have the polynomial, so let's find what the zeros are. So set the left-hand side equal to 0. Alright, so we have x minus 5 times x minus the square root of 2 times I times x plus the square root of 2 times I. We're going to set each of these factors equal to 0. So x minus 5 equals 0. X minus the square root of 2 times I equals 0, and x plus the square root of 2 times I equals 0. Alright, and so we're going to have x equaling 5. We have x equaling the square root of 2 times I, and we have x equaling negative the square root of 2 times I. Alright, so these right here are my zeros. Alright, my x-intercept, erase. Alright, my x-intercept is going to be at x equaling 5, and that's it, because the square root of 2 times I and negative square root of 2 times I, those are non-real. So this is my only x-intercept here. Alright, I'm going to pause this real quick and erase this so we can write the polynomial in standard form next. Okay, so we're going to write f of x in standard form. So that's going to equal x minus 5. Okay, I have here again a difference of squares, so this is going to be x squared and then minus the square root of 2 times I squared. So I'm going to have f of x equaling x minus 5 times x squared. Now I have the square root of 2 squared, so the square root of 2 times the square root of 2 is the square root of 4. The square root of 4 is 2. Right, and then I squared equals negative 1. So 2 times negative 1, so I'm going to be subtracting a negative 2. So f of x equals x minus 5 times x squared plus 2. Alright, and now I have to go ahead and FOIL, so f of x is going to equal x cubed plus 2x minus 5x squared minus 10. Put it in standard form with my degrees in decreasing order, so I have x cubed minus 5x squared plus 2x minus 10 as my answer. Okay, finally for the last one, part C here, again we want to find the zeros. So by now you should know kind of the pattern. So my zeros are going to be x equaling 3, x equaling 3, x equaling I, and x equaling negative I. Alright, so x equaling 3, that 0 has a multiplicity of 2, so at the x-intercept x equaling 3 I'm going to have a bounce. And so my x-intercept is x equaling 3. Right, and then x equaling I and x equaling negative I, those are non-real zeros, so those aren't going to intersect the x-axis. Alright, so zeros and x-intercept. Okay, what I have to do next is put this in standard form. So I got a perfect square trinomial here. Alright, so I'm going to have x squared minus 6x plus 3. Got a difference of squares here, so it's going to be x squared minus I squared. And so I have x squared minus 6x plus 9 times x squared. So I squared again is negative 1, so minus a negative 1 is going to be adding 1 there, so I have x squared plus 1. Alright, and now I got to go ahead and expand this by distributing. So x squared times x squared gives me an x to the 4th. X squared minus 6x, that gives me a negative 6x cubed plus 9x squared. Alright, and then plus x squared minus 6x plus 9. Alright, so it's going to leave me with x squared minus 6x cubed, 9x squared plus 6 plus x squared, that gives me a positive x squared minus 6x plus 9. Alright, so there's the polynomial written in standard form. Okay, the next thing we're going to kind of talk about is the complex conjugate theorem. It says that roots or zeros that are not real are complex with an imaginary component. Complex roots with imaginary components always exist in conjugate pairs. Alright, so if a plus bi, where b doesn't equal 0, is a zero of a polynomial function, then its conjugate, a minus bi, is also a zero of the function. So what this is saying is if I have a 0 that is 3 plus 2i, then I know automatically that 3 minus 2i also has to be a 0. So let's use this in example 2 here. We have to write a polynomial function of minimum degree in standard form with real coefficients whose zeros include -3, 4, and 2 minus I. Now, since 2 minus I is a 0, we know that from the complex conjugates theorem that 2 plus I is also going to be a 0. Alright, and so now what we're going to do is work backwards to write this polynomial function. Alright, so let's write these zeros in terms of as their linear factors here. So we're going to have f of x equaling x plus 3 times x minus 4. Alright, and then we have 2 minus I. Alright, and we have to write that in terms of a linear factor. Alright, so we know that x equals 2 minus I, so we know that x equals, let's get rid of x equals. So we know that x minus 2 plus I is going to be a linear factor. Right, and then x equals 2 plus I, should be an I there. Right, so x minus 2 minus I, that's also going to be a linear factor. Alright, and so I have my 4 linear factors here. Now what I'm going to have to do is go ahead and FOIL these first two. Alright, and so I have f of x equaling x squared plus 3x minus 4x minus 12. So that's going to equal x squared minus x minus 12. Alright, and now what I'm going to have to do is go ahead and expand these out. Alright, and so I'm going to need some more room. Okay, so I just erased a little bit, alright, and just, this is what we calculated just a little bit ago. Alright, so now I have to take x and multiply it by all three terms, -2 and -I, and multiply it by, again, all three terms here. Alright, so I have x times x, that's going to give me an x squared. X times -2 gives me a -2x, plus I times x. And then I have -2 times x, so it's -2x. -2 times -2 is a positive 4, and then minus 2 times I. And then I have a negative I times x plus 2I minus I squared. Alright, and so I'm going to have f of x equaling x squared minus x minus 12, and then I have to simplify here. Alright, so I am going to have an x squared. Alright, and then I have a -2x and a -2x. Alright, so those are the real parts with my variable x. So that's going to give me a -4x. Let's see here. Now I have a negative I times x and a positive I times x, so those cancel. Alright, I'm done with these. Alright, so I have a positive 2i and a negative 2i, and so I'm left with 4 minus I squared. Alright, so this is a negative times a negative 1, so that's really going to be a positive 1, so 4 plus 1, that's going to give me a positive 5 here. Alright, and now, again, this is this is a long one, but now I gotta go ahead and distribute again. So x squared times x squared gives me x to the 4th minus x cubed, alright, minus 12x squared minus 4x cubed, don't make a mistake, plus 4x squared plus 48x. Alright, plus 5x squared minus 5x minus 60. Alright, so I think we're good there. Now we just have to combine like terms. So I'm going to have an x to the 4th. Alright, so I have a negative x cubed and a negative 4x cubed, so that's going to give me a negative 5x cubed. Let's see here. X squared, so I have a negative 12x squared and a positive 4x squared, so that's negative 8. And then a positive, so that's going to be a negative 3, so minus 3x squared. 48x and a negative 5x, so that's going to be a positive 43x minus 60. Alright, and so it was a lot of work, but there's our polynomial written in standard form, and we found that out just by knowing what the 4 roots or my 4 zeros were. Okay, example 3, I'm going to get you kind of started on this, and I would want you to pause and finish it on your own. Alright, but we want to write a polynomial function of minimum degree in standard form with real coefficients whose zeros include x equals 1, x equals 1 plus 2i, and x equals 1 minus I. So the same as the problem before. So my zeros, alright, I have x equaling 1, I have x equaling 1 plus 2i. Now by the conjugates theorem, complex conjugates theorem, we know that x equaling 1 minus 2i is also going to be a 0. Alright, and then I know that x equals 1 minus I is a 0. So I know that x equaling 1 plus I is also going to be a 0. Alright, so 1, 2, 3, 4, 5. Alright, so I should end up here with a degree 5 polynomial based on the number of complex roots that I have. So go ahead and press pause, alright, and try and knock this one out. Alright, it's going to be long like the previous one, but let's see if you can get the right answer. Okay, so if you got f of x equaling this, alright, then you're correct. Alright, so this is the right answer. This is the polynomial written in standard form for example 3. Okay, in the last example on this video, we want to find all real zeros of this polynomial f of x and write f of x in its linear factorization. So what you want to do here and how we're going to solve these is you want to put this into your graphing calculator and graph it. You're going to get a picture that looks something like this here, and what you want to do is identify what the real roots are. Alright, so x equaling -2, x equaling 1, and x equaling 4. Alright, those are my x-intercepts. Those are going to be the real roots. And what I'm going to do is use synthetic division to take this from a degree 5 polynomial, alright, to a quadratic, and then use my methods to solving quadratic equations to find what the imaginary roots are, because I know that I'm going to have 2 imaginary roots because I have 3 real roots. And again, this is the degree 5, so there needs to be 5 total. Okay, so again, here's my polynomial, here are my zeros, and I'm going to use synthetic division. Alright, so I'm going to write the coefficients, so 1, -3, -5, 5, -6, and 8. And then in the box, I'm going to put -2. And now I'm going to bring down the 1. And then I'm going to multiply and then add. So -2 times 1 gives me a -2. So this is -5. This is going to give me a 10 and a -5, a 10. Actually, no. This is +5. So this is going to be 5, and then this is -10. This is a -5. This is 10. This is 4. And then this is -8. And then this is 0. Alright. So here now I have a quartic. Alright, so my goal is to get this, use synthetic division 3 times to make it quadratic. So I'm just going to keep these here, and now I'm going to put, what was my other 0? I'm going to put 1 in the box. Alright, so bring the 1 down, so 1 times 1 is 1, and that gives me a -4. 1 times -4 gives me a -4, gives me 1, 1, -4, -4, and 0. Alright, and then I'm going to divide synthetically one more time, so the resulting polynomial is going to be quadratic. So 1, that's going to give me 0 here, 0, 1, 4 times 1 gives me a +4 and 0. Alright, and so this is going to be x squared plus 0x plus 1 here. Alright, and so I'm going to have f of x equaling I'm going to need a little bit more room, so let's do, where can I write this? So f of x is going to equal x squared plus 1 times x plus 2 times x minus 1 times x minus 4. Alright, and I want the linear factorization. Alright, so I'm going to pause this because we're going to have to take this and break that down into 2 linear factors. Alright. Okay, so I rewrote this on a new page, and what we want to do is break that up into 2 linear factors. Alright, so I'm going to have x squared plus 1, and I'm going to set it equal to 0, so I'm going to have x squared equaling -1, take the square root of both sides, and so I have x equaling plus or minus the square root of -1. Well, the square root of -1 is I, so x equals plus or minus I. Right, and so my polynomial, written as sheerly it's linear with linear factors, is going to be x plus I times x minus I times x plus 2. I'm going to erase this. times x minus 1 times x minus 4. Alright, so that wraps up the first part of the 2.5 lesson. Be ready for the homework tomorrow. Again, this is the final lesson before we take we break it up and take the chapter 2 part 1 test.